Hi guys, I'm Monica. Welcome back to my channel Aeroker. So in this journey of aerodynamics, as we proceed further, in this video we are going to have a look at non-lifting flow over a cylinder. So without any further delay, let's get started. So for non-lifting flow over a cylinder, what we are going to do over here is we are going to add a uniform flow which is with velocity v infinity over here, and a doublet which is of strength K. Now as you can see, the direction of doublet is upstream, which is facing into the uniform flow. Now let us write the stream function of both the flows, that is uniform flow and the doublet. For uniform we have v infinity r sine theta, and for the doublet we have psi is equal to minus k by kappa by 2 pi sine theta by r. So the combination of these two would be this, which you're able to see on the right, that is the non-lifting flow over a cylinder. So the combined stream function can be given as v infinity r sine theta minus kappa by 2 pi sine theta by r, or we can also write it as psi is equal to v infinity r sine theta 1 minus kappa by 2 pi v infinity r square. This is kappa. Let us say this is our equation 1. Now over here we'll introduce one new variable, that is capital R square, and let us say that this is equivalent to 2 kappa by 2 pi v infinity. Alright, so if I'm going to substitute this R square and manipulate equation 1 mathematically, that results into psi is equal to v infinity r sine theta multiplied by 1 minus capital R square by small r square. This is our equation 2. Now, since then I'm saying non-lifting flow over a cylinder, non-lifting flow over a cylinder, but how is the flow non-lifting is what we have to look, but that we will come to know at the end of our lecture. So this, what is this equation 2? This is our stream function for the combination of uniform and doublet. So it is also the stream function for the flow over a circular cylinder which has a radius r, as you can see over here. Okay. Now let us differentiate this equation 2 in order to obtain velocity field. So in order to obtain velocity field, I have Vr is equal to 1 by r dou psi by dou theta, which is 1 by r v infinity r cos theta into 1 minus r square by small r square. So upon taking Vr and differentiating, and v theta and differentiating, we obtain the velocity field, that is Vr and v theta. Let us say this is our equation 3 and equation 4. Now what is the next task? To calculate the stagnation points. Now in order to calculate the stagnation points, what are we going to do? Set these two equations, that is equation 3 and equation 4. The velocity is equal to 0, which means there is zero velocity, that is nothing but stagnation point. So I have 1 minus r square by r square. V infinity cos theta is equal to 0, and the next would be 1 plus r square by r square. V infinity sine theta equal to 0. If I simultaneously solve both these equations for r and theta, the stagnation points located at r comma theta are given by one would be r comma 0 and the second would be r comma pi. So these 2 points are denoted as A and B, as you can see here in the figure. Now, the equation of the streamline that is passing through stagnation point B, how can I obtain that? So, in order to obtain that, what we are going to do is inserting the coordinates of B into equation 2. That is, the coordinates of equation B we are going to put in equation 2. So let us substitute and see what it yields. That is nothing but what do we have over here? R is equal to R, correct? And theta would be equal to pi. Small r is equal to R and theta is equal to pi. So upon substitution in equation 2 over here, I would get psi is equal to 0. So similarly, if I put the coordinates of A in equation 2, that will also give me psi is equal to 0. So when I say that psi is equal to 0, what does that mean? We can conclude that the same streamline goes through both the stagnation points A and B. That is the conclusion we get by substituting the stagnation points in equation 2. That is the stream function. Alright. Now, the equation of streamline, if I were to write the equation of streamline, because I'm getting psi is equal to 0, I can simply write it in this way. B infinity r sine theta 1 minus r square by r square is equal to 0. Let us say this is our equation 7. Now this equation 7 is satisfied by small r is equal to capital R for all values of theta. Now we know that r square is equal to kappa by 2 pi v infinity, and this is a constant. If I consider the case of polar coordinates, where in that case, in case of polar coordinates, small r would be constant, which is equal to capital R, correct? And this would give me the equation of a circle with radius r, correct? As you can see here in figure 1, we have a circle with radius r. So which means this equation 7, what I have got, it describes a circle with radius r. So equation 7, this equation 7 is satisfied when theta is equal to pi and theta is equal to 0 for all values of small r. Hence, whatever the horizontal axis is passing through points A and B, extending infinitely far upstream and downstream, is part of the stagnation streamline if I extend that far upstream and downstream. Now there is one point to be noted over here. The psi equal to 0 streamline we have, right? Because this is, since it is going through the stagnation points, it is dividing the streamline, correct? So which means all the flow that is inside the psi equal to 0 circle, which you are able to see over here, the circle which we have, which indicates over here that the psi is equal to 0, whatever the flow is inside this circle becomes doublet, and all the flow that is outside this circle is psi is equal to 0. Whatever flow is outside this circle becomes uniform. Okay. So now we can replace this flow inside the circle by a solid body, correct? And the external flow will not know a difference, because inside this circle the flow is doublet. Other than that, the flow is uniform over here. Similarly, the inviscid irrotational incompressible flow over a cylinder of radius r can also be synthesized by adding uniform flow with velocity v infinity and doublet of strength kappa. And in that case, what would be my R? R would be under root kappa by 2 pi v infinity. Let us say this is our equation 8. But note down, this is for inviscid, irrotational and incompressible flow. So points to be noted over here are that from equations 1 to 4, as we proceed from equation 1 to 4 over here, we see that the entire flow field is symmetrical about both horizontal and vertical axis. That is what you are able to see in the figure as well here. Correct? Through the center of the cylinder, which is clearly shown by this streamline pattern. So which means that my pressure distribution is also symmetrical about both the axes. So what happens when I say the pressure distribution is symmetrical about both the axes? That is over the top of the cylinder and over the bottom of the cylinder, which means the pressure is being balanced. That is, the pressure at the top of the cylinder is being balanced by the pressure distribution over the bottom of the cylinder. So when there is a balance of pressure, there is no lift created. So this generation of lift part we will be also seeing in future when we will consider the airfoils. So lift is a thing or a component, or lift is a force which is generated only when there is a pressure difference. So now as we see, there is no pressure difference over here, which means there is no lift being generated. This means I can call this flow as a non-lifting flow over a cylinder. Now this was the story of top and bottom. Let us consider the front and back. The front part, that is this part, this area, and the behind part. So the pressure distribution over the front of the cylinder is balanced by the back of the cylinder, which means there is no net drag as well. So we can say that net lift is equal to 0 and net drag is equal to 0 over here. So which means there is 0 drag and 0 lift. But are we okay with this statement, or is there something which is contradictory, which is not acceptable in these statements? 0 lift? Yes, it is possible. Yes, we can accept that as a real life case where there is 0 lift. But 0 drag, is this something which can be accepted practically? No, certainly not. It is not possible in real life that the net drag is 0. There will be some amount of drag exerted by the body, exerted on the body. So whenever any aerodynamic body is immersed in a real flow, any aerodynamic body for that matter, it will experience a drag. So this paradox between the theoretical result of 0 drag and in real life the drag is finite, this was encountered first in 1744 by a person, a scientist named Jean-Le Rond d'Alembert. Okay, so after the scientist noted this, from then it came to be known as D'Alembert's paradox, which is one of the most important term used in aerodynamics. So now, as discussed, D'Alembert was the first person to know this difference. Now, this inviscid theory, it predicts that the flow is smooth behind the cylinder, there are no wakes, and it leaves the cylinder smoothly, and there are no symmetries which result in 0 drag. But as we saw, that is not the real case. So in order to quantify this discussion, what we are going to do is, now we know the velocity distribution from equation 3 and 4, correct? So what we will do is, in these equations 3 and 4, we will put r is equal to r, that is small r is equal to capital R. And if I put that in equation 3 and 4, let us see what that results in. That would be VR would result in being 0. Let us say that's our equation 9. And V theta would be minus 2 V infinity sine theta. Let us say this is our equation 10. So by observing these equations 9 and 10, what is it that we can say? So at the surface of the cylinder, VR is geometrically normal to the surface, correct? So equation 9 is consistent with the physical boundary condition that the component that is velocity normal to the stationary solid must be 0. So we have VR as 0. Then we have equation 10, which is giving the tangential velocity, which is the full magnitude of velocity on the surface of the cylinder, which is given by V theta is equal to minus 2 V infinity sine theta, which we can also say as V on the surface. Now, with this velocity, there is something to be noted over here, that is the minus sign. Now, how do we get about this minus sign? Why is this minus sign here? So, according to the sign convention, if we have a look, in the polar coordinates, V theta is positive in the direction of increasing theta. That is in the counterclockwise direction. As you can see, this is in the increasing and it is in the counterclockwise direction. This is your R, and over here V theta is positive. Now if we go back to figure 1 over here, if I say the surface velocity for 0 to pi, if I consider the range for theta as 0 to pi, which means it is obvious in the positive direction of increasing theta. So which means my minus sign is correct. It is appropriate. If I consider the range of theta between pi to 2 pi, then what happens in the case of surface flow? It is in the same direction as increasing theta, but here the sine theta is itself negative. So once again the minus sign is justified in equation 10. So from this we see that the velocity that is being given in equation 10, at the surface it reaches a maximum value of 2 into V infinity. When will it reach a maximum value? When there are two values of theta. One is theta is equal to pi by 2 and the other is 3 pi by 2. Now what are these surfaces? Where do I have 2 V infinity? One would be this point and the other would be this point. So these are the 2 points where I would have my maximum velocity. So this is your R and this would be your theta from the center. So these points of maximum velocity, what we are observing for the entire flow field, are over here. That is the top and bottom of the cylinder. Okay. Now let us introduce one more quantity, that is Cp. Now we know the basic formula for Cp, which is given by 1 minus V by V infinity whole square. Let us say this is our equation 11. Now what if I compare equation 10 and 11? So if I combine equation 10 and 11, my Cp would result in 1 minus 4 sine square theta. This is the result we get upon mathematical manipulations. Let us say this is our equation 12. What does this give me? This gives the surface pressure coefficient over a circular cylinder. Now, based on this equation, we have a graph over here that you can see, which says the value of varying Cp. Now, the value of Cp varies from 1 at the stagnation point to -3 at the points of maximum velocity. So as you can see over here, where the point 1 is indicated over here, that is your stagnation point. Okay. Now here you can see this part indicates the bottom half of the cylinder, top half of the cylinder, rear half of the cylinder, front half of the cylinder. So the regions that are corresponding to the top and bottom half of the cylinder are these, as you can see. And also you can see the range of Cp with respect to theta. Now, the pressure distribution over the top half of the cylinder is equal to the pressure distribution over the bottom half of the cylinder. Hence, the lift must be 0. Correct? And similarly, the regions that are corresponding to front and rear halves of the cylinder, what is happening over here? The pressure distributions are same. So theoretically, my drag becomes 0. So with the help of graph, this is the theoretical result what we are having a look at. Now, we have here the integral forms of force and moment equations. Okay, so if we are considering an inviscid flow, as we said, the drag is 0. The drag is assumed to be 0 in case of an inviscid flow. So when I say inviscid flow, Cf, which is the coefficient of drag, becomes 0 over here. So when I say Cf is equal to 0, what happens to the above equation Cn over here? So after substitution of Cf is equal to 0, we are remaining with the part. So after substituting Cf is equal to 0, these are the equations that we get. Let us say this is our equation 13 and 14. Now, for a circular cylinder, as we have considered a circular cylinder over here, the chord C, these are the equations usually that are considered for an airfoil, which represent the forces and moments over an airfoil. So because we are considering a cylinder over here, the chord C, which is denoted by the term C, would represent the horizontal diameter in case of a cylinder. Okay. So now, by looking at this figure, we can say that CPL and CPU are equal. That is, CP for the bottom surface and the upper surface are equal, which are measured corresponding along the chord, that is the radius over here, the horizontal radius. So which means if they are equal, CPL and CPU are equal, then what happens to the integrands in the equation 13 and 14? They go to 0, which means my Cn is equal to 0 and Ca is equal to 0. So the coefficient of lift Cl in terms of forces is given as Cn cos alpha minus Ca sin alpha, and CD is given as Cn sin alpha plus Ca cos alpha. So when we are saying Cn and Ca are 0, which in turn gives me that Cl and CD are 0. Hence, with the help of integrands and force and moment equations also, theoretically we are showing that the coefficient of lift and drag are 0, which in turn means that the lift and drag are 0 over here. But this is the case for an inviscid incompressible irrotational flow. So this is it about non-lifting flow over a cylinder. Thank you for listening. Stay tuned.